In this chapter, we're going to be going over an introduction to vectors. So starting with some definitions here. So scalars are real numbers, and they only involve magnitude, such as pounds or speed. And for vectors, the difference with vectors is that vectors include both magnitude and direction. So examples of vectors are going to be something like velocity, acceleration, and force. And comparing the two, if we have something like 30 miles per hour, that is a speed, which is a scalar. If we say 30 miles per hour east, that's going to be a vector because direction is included. And typically vectors are going to be represented with a directed line segment. So directed meaning there's going to be an arrow on the end of one of the sides of the arrow. So for example, we have this line right here and we have 10 pounds, and then the direction in this case is given to us as an angle of 30 degrees. When we are writing vectors by hand, we're either going to use the little notation where we put an arrow over it, or we're going to use a boldface font. So obviously if we're just writing it by hand, we're just going to have to put the arrow over it because we can't, it's kind of hard to write boldface when you're writing with your hand. Okay, so just know that both of those notations mean the exact same thing, and the order does matter for OP. The first letter indicates where it's starting, the initial point, and the second letter indicates the terminal point. So what that means is that the vector OP does not equal the vector PO. We can see here in this little diagram, OP looks like this, where the arrow is going towards P, and then PO looks like this, where the arrow is going towards O. And they are the same magnitude, but they actually have opposite directions. And two vectors are equal if and only if they have the same magnitude and the same direction. So you can see over here, we have vectors A and B, same magnitude, which means the same length and the same exact direction. And C and D here are also equal, same direction, same magnitude. But then over here, we have E and F. They are not equal. They look like a different magnitude and a different direction. Okay, now getting into vector operations and starting with adding vectors. So it's going to be the sum of two vectors. So when we add two vectors, the result is going to be also a vector. And there's going to be two ways that we can geometrically think of this. The first method here is going to be place the initial point of vector B at the terminal point of vector A, and then the vector with the same initial point as A and the terminal point as B is going to be the sum A plus B. So if we have a vector A that looks like this, and then we have a vector B that looks like this, and we were adding them, you put B, the initial point of B, at the terminal point of A, and then this vector right here from the beginning of A to the end of B is the sum A plus B. And method 2 here is going to be what we call the parallelogram rule. We're going to place vectors A and B so their initial points are at the same spot. So something like this. Here's vector A. Vector B is coming off of that same exact point. And then we're going to fill in this parallelogram. So we have to remember parallelograms are going to be opposite sides are congruent. So this next side right here is also side A, and then this side over here is also side B. So we fill in those sides, and then the diagonal of the parallelogram is going to be the sum A plus B. Okay, and then a couple properties here. The vector addition is commutative, which means the order doesn't matter. So A plus B equals B plus A, and the vector sum A plus B is called the resultant. And then that brings us to vector subtraction. For every vector that we have, which we'll just call it V, there's going to be a vector negative V that's going to have the same exact magnitude but the opposite direction. And the sum of V plus negative V is going to have a magnitude of 0, which is called the zero vector. So when we're subtracting vector B from vector A, that means we're going to be doing A minus B. What we're actually doing is finding the sum A plus negative B. Okay, so when we do that geometrically here, we have this vector A, and if this is vector B down here, but we are subtracting A minus B, first we have to find negative B. So negative B is just going to have the opposite direction as positive B. And then when we add A plus negative B, we do exactly what we just did before. And this method right here is the parallelogram rule. And we just complete the parallelogram, and then the resultant here is the sum. And then next we have scalar multiplication. So scalar multiplication is just multiplying something by a number. We're going to be calling a scalar, representing it with a lowercase k. So when we're multiplying a scalar k times u, we get the vector ku, and all this means that it's k times greater in magnitude than the original u. So for example, if we have this vector u, and we multiply it by 2, that's going to give us double the length, double the magnitude of the original. If we have 3/2 times u, that's going to be 1.5 the magnitude, or 1.5 the length of u. If we have 1/2 of u, that's going to be 1/2 of u. It's going to be u divided by 2. And then if we have negative 2u, it's going to be 2 times the magnitude in the opposite direction. So just notice that the arrow is in the opposite direction here. And now we're going to be thinking about vectors in the xy coordinate system here. So a vector with its initial point at the origin in the rectangular coordinate system, which once again is just the xy plane, is called a position vector. So initial point at the origin is called a position vector, and a position vector u with its endpoint at the coordinates a comma b is going to be written with those kind of brackets, a comma b. So if you see just a vector denoted as u, that's the same as if you denote it as a b with those brackets on it. This means that every vector in the real plane is going to correspond to an ordered pair of real numbers. So geometrically, a vector is a directed line segment, from which we already saw, and then algebraically you can think of it as an ordered pair. So here is what it would look like. This is going to be the position vector because the origin is the initial point, and then its magnitude goes until it gets to the point a comma b. So we can call this vector AB. So if we were only given the point AB, we can find the magnitude of the vector, because we have to remember the magnitude is just the length. So that would be creating a right triangle and then doing the Pythagorean theorem. A squared plus b squared equals u squared in this case. So if we ended up solving this for u, we'd have to take the square root of both sides, and we get this as our this is our magnitude. It's going to be the absolute value is going to equal the square root of a squared plus b squared. So that's how we can find the magnitude of the vector, only given the point. And then we can also find the angle. So we can see this angle up here in the little diagram. We can find that angle, the direction angle we call it. It's going to be just using SOHCAHTOA. We have the opposite side of b and the adjacent side of a, so it's going to be tangent of theta equals b over a. So we can solve that for theta by doing the inverse, tangent inverse on both sides. That's theta equals tan inverse of b over a. Okay, let's do an example here. Let's find the magnitude and direction of u, of the vector u, which is 3, -2. So if we were to draw it out, it would look like this in quadrant 4 here. And finding the magnitude, we know that that's going to be the square root of a squared plus b squared. And once again, that's because if we created a right triangle in here, this would be side A, this would be side B. So using the Pythagorean theorem, a squared plus b squared equals u squared. Solve for u, square root on both sides. But all we have to do here is just plug on in. So it's going to be the a value is 3, and then the b value is negative 2. So that's going to be 3 squared plus negative 2 squared. And that's going to give us 9 plus 4. So we get the magnitude of u, the length of u, is going to be the square root of 13. Okay, so we can just leave it like that. And then let's find the direction angle. And we know that that's going to be, I'm just going to skip to having theta solved for. Theta equals tan inverse of b over a. That's going to end up being theta equals tan inverse of negative 2 over 3. So before we actually evaluate this, let's just make sure where we know the angle is that we're solving for. The angle is this angle right here. Always going to be from the positive x-axis going counterclockwise to that vector. So that's the angle that we're looking for. So when we type this in the calculator, and let's have this in degrees, we're going to get about negative 33.7. So that is obviously not our angle, right? Negative 33.7 is going to represent this angle right here. It's going to be that reference angle that's inside that triangle. So in order to get our angle, that's actually going to be a coterminal angle. And in this case, we're going to have to add 360 degrees to it. Okay, so that one was a little bit tricky because we had to know to add 360 degrees, but we get 326.3 degrees. So that's the magnitude and direction of that vector. So this time we're going to be going in the opposite direction. We're going to be given the magnitude and the directional angle for the vector, and then we're going to find the components A and B. So it's the same idea using a trig here with a right triangle. If we have the magnitude and directional angle, then the A component is going to be the absolute value of u, which is the magnitude, times the cosine of the angle, and B is going to be the magnitude of u times sine of the angle. So what that means, if we want to write u using our components A and B, it's going to be the magnitude times cosine for A, and then the magnitude times sine of theta for B. So let's go ahead and see this example. So vector W has magnitude of 25 and a directional angle of 41.7 degrees. Find the horizontal and vertical components. So drawing it out, it's going to look like this. We know it's in the first quadrant because 41.7 degrees is between 0 and 90 degrees. So what we're actually doing here is we're essentially looking for the x and the y value, and we're trying to find this ordered pair, A comma B. So we can create a right triangle if you want, and then solve for A and B, and you can see how we get those formulas above. But let's just go ahead and use them. So let's find A, absolute value of u times cosine of theta, and that is going to be the absolute value of 25 times cosine of 41.7 degrees. So if we go ahead and type that in the calculator, we're going to get 18.7. So that would be the x coordinate. Let's go ahead and do it for B. So the magnitude of u times sine of theta, and that's going to be 25 times sine of 41.7 degrees. And we type that in the calculator, and we get B equals 16.6. So that means we can write vector W as the vector 18.7 comma 16.6 using those correct brackets on the end. Now we're going to do some more operations with vectors. So this little table here shows us all the important things. If we are adding two vectors together, then that means we add their first components for the new first component, and we add their second components for the new second component. If we're doing scalar multiplication, then we have to multiply each component by that scalar. And if we have positive u having components a1, a2, and we negate it, then that just means we have to negate both components. And for the last one here, if we're subtracting two vectors, AB minus CD, that's the same as just subtracting the first components and subtracting the second components. Okay, so pretty simple operation. So let's go ahead and do some examples. So let's let u be the vector -2, 1, and v is 4, 3. And we have this graph below to show here's v and here is u. And let's go ahead and do these problems. And let's also draw them out. So we're going to be drawing the result. So for a, it's u plus v. So let's go ahead and just evaluate this. So writing it out in this format, it's going to be -2, 1 plus 4, 3. All we have to do is add the first components, add the second components. So it's going to be -2 plus 4 for the new first one, 1 plus 3 for the new second one. That gives us the result 2, 4. So that's going to be the sum of those vectors. Let's go ahead and draw it out. And I'm actually just going to draw it out on the graph that we already have over here. So 2, 4, we can see that that's going to be up here. It's going to be this point up here. So that's going to be this vector u plus v. And we can tell that that makes sense because if we went ahead and did that parallelogram rule, then this would be finishing the parallelogram over here, and then this would be finishing it on this side, and then we would put the initial point where u and v started, and then the resultant is the diagonal, which we can see is true. Or we could have done it the other way, and we could have added vector u to the end of vector v, which would have been like that. And then we could have connected them from beginning to end, and it would have been the same exact thing. So just kind of a check geometrically to make sure our answer makes sense. Okay, next one we have -2u. So writing this out, we can write it out as -2 times vector u was -2, 1. That means we have to multiply each component by -2. Obviously we can do these in our head without writing the whole thing out. So that's going to end up giving us, oops, that should be times -2. That's going to end up giving us +4, -2. So that's going to be a vector that's twice the magnitude of u, but in the opposite direction. So let's go ahead and plot that out to check. So that's 4, -2, that will be down here. And we can see that it is in the opposite direction of u, and it does look like it's about twice the magnitude of it. Okay, the last one, we have 3u minus 2v, so a little bit more complicated, but still not too bad. So it's going to be 3 times u, which was -2, 1, minus 2 times v, and v is 4, 3. So we just have to combine both of those methods that we just did in the previous two. We're going to multiply both components of u by 3. That's going to give us -6 and 3. And then subtracting 2 times v, we're going to multiply both components in v by 2. That gives us 8 and 6. And all we have to do now is just subtract the components, component-wise. -6 minus 8 gives us -14. 3 minus 6 gives us -3. So that is the vector -14, -3. So I'm not going to graph this one because it won't fit on this graph above, but obviously it's just as easy as the other ones. You're just plotting an ordered pair and connecting it from the origin with a directed line segment. So now for some more important definitions with a unit vector. A unit vector is going to be a vector that has a magnitude of 1. So it's a length of 1. And two of the main ones that we're going to be using here in the xy plane are going to be the unit vector I and the unit vector j. And the unit vector I is going to be the point 1, 0, and then j is 0, 1. So if we plotted out I, it would actually look like this: x coordinate of 1, y coordinate of 0. And then similar for j, where it is on the y-axis with the coordinate 0, 1. Okay, so the idea for this, the importance is that using these, we can express any vector we want to, a comma b, in the form ai plus bj. So let's see an example here. Let's write the vector w, which is 4, 3, in the form ai plus bj. It's relatively simple. We just have to recognize that w is written in the form a comma b, and all we have to do is plug in 4 as a, 3 as b into here, and that'll give us our result. So that's going to end up being w, vector w is 4i plus 3j. And for the vector notation with the arrows over the top, with I and j, I just kind of replaced the dots with just the arrow. So it's just as simple as that, just inputting your a and b in there. And let's check why this is the case. So I'm just going to put a little check here. If we have 4i plus 3j, that's the same thing as replacing I with 1, 0, and then replacing j with 0, 1, just based on what we define them to be right above. And we can go ahead and do scalar multiplication in addition. That's going to be 1 times 4, 0 times 4, and then 0 times 3, 3 times 1. And then all we have to do is add these up. 4 plus 0 is 4, 0 plus 3 is 3. So we can see that that is exactly what we started with in the beginning of the question. Okay, so it's just important that we know how to convert between both of these notations. They mean the exact same thing. So far we've done adding vectors, subtracting vectors, and those both gave us an answer that was also a vector. So now what we're going to be doing is multiplying vectors. This is only one way to multiply vectors. There's another way. So this is the dot product. When we do the dot product, the answer is a scalar. So we're actually not going to get a vector out as our answer. We're going to get a scalar. There is other ways to do this, but for now we're just focusing on the dot product. So the dot product between two vectors, u and v, is going to be denoted with a dot. So it's multiplication, but we have to make sure we're using the dot form of multiplication for this. And you can read it as u dot v. It's going to be given by this formula. It's pretty simple. All you have to do is multiply the components by the other one's same component, and then add the results. So it's going to be AC plus B times D. So first component times first component plus second component times second component. Okay, let's do an example here. So we have 2, 3 dot 4, -1. And when we're multiplying these together, we have to do component-wise. That's 2 times 4 plus 3 times -1. So first component times first component plus second component times second component. That gives us 8 plus -3. So 8 minus 3 gives us a scalar value of 5. So it is not a vector. And let's do one using the unit vector form. We have 6i plus 4j dot negative 2i plus 3j. But we just have to do the same thing. We don't need to incorporate the i's and the j's. We just have to do first component times first component plus second component times second component. That's negative 12 plus 12. That actually gives us a dot product of 0. So let's go over some properties here and kind of what those values mean. So for some properties of the dot product, if we are doing the dot product between two vectors, it's commutative, so u dot v is the same as v dot u. If we are adding two vectors and then doing the dot product between another one, that's the same, it's kind of essentially the same as distributing. So we can distribute the vector w and we get u dot w plus v dot w. And if we do the vector 0 dot u, that's always going to give us a scalar vector, a scalar quantity of 0. And this one over here is essentially the same one as distributing, as we already saw. And if we are doing a vector times a scalar and then dotting that with another vector, that's the same as doing the dot product with the vectors first and then multiplying by the scalar, or it's the same as multiplying the scalar on the other vector first. Okay, and then the last one here, if you dot a vector dot itself, then you get the magnitude squared. And then some other properties here is the dot product can be positive, negative, or 0. So something where it's going to help us find a value of something here is going to be finding the value of an angle between the vectors. So if we have two vectors, here's vector u, here's vector v, and let's say we wanted to find the angle between them, which is denoted with theta. This is where the dot product comes in handy. So this is going to be the formula we're going to be using. So if theta is an angle between u and v, between 0 and 180 degrees, that means u dot v equals the magnitude of u dot, or times the magnitude of v times cosine of the angle. And if we're trying to solve this for cosine, you'd have to divide by magnitude of u and v. You get cosine of theta equals u dot v divided by the magnitude of u times the magnitude of v. And as we know, if we're trying to solve this for theta, it's going to be theta equals cosine inverse of the other side. So cosine inverse of u dot v divided by the magnitude of u times the magnitude of v. Okay, let's go ahead and do an example here. Let's find the angle between these two vectors, and let's go ahead and draw this out first. So plotting or graphing vector u and vector v, it would end up looking something like this, and we're looking for theta. We're looking for the angle between these two vectors. So let's go ahead and use that definition. I'm going to use the form where we already have theta solved for. So theta is cosine inverse of u dot v divided by magnitude of u times magnitude of v. So just kind of a little side note, I put the little multiplication dot down here. Those are two scalar values. That's just going to be a number times a number. In the numerator, that is the dot product between two vectors. Okay, so all we have to actually do here is plug in some values. I just drew I just graphed those just so we see how they look like. So it's cosine inverse of u dot v. So maybe let's do u dot v on the side. It's going to equal first component times first component plus second component times second component. That's going to give us 6 plus 4. So u dot v, the dot product here gives us 10. So that's going to be the numerator. So it is 10 divided by the magnitude of u times the magnitude of v. So just a little bit of side work for those as well. Magnitude of u, this is the formula from earlier. It's the square root of first component squared plus second component squared. That's going to be the square root of 3 squared plus 4 squared, which gives us the square root of 25, which is going to give us 5. So that's the magnitude of u. And now let's do the same thing for the magnitude of v. So same formula. It's going to be the square root of a squared plus b squared, which is going to give us the square root of 2 squared plus 1 squared, which is the square root of 5. So we can leave it just like that. So that's going to be the other part in the denominator here. So this is going to end up being theta is cosine inverse 10 over 5 is 2. So I'm just going to write that as 2 over radical 5. Just simplify that fraction a little bit. So plugging this in the calculator is going to give us 26.57 degrees. So it seems pretty reasonable. If you take a look at that angle, it looks like it's 26 degrees is a pretty good, a pretty reasonable value to get. Let's do one more example here. So we have u is the vector 2, negative 6, and v is the vector 6, 2. And if we graphed these out, it would look something like this. And we're trying to find this angle between them, theta. So let's go ahead and write down the formula. So same formula that we just used, and we need to find the same values that we just found before. So let's find the dot product u dot v. That's going to be first component times first component plus second component times second component. And that's going to give us 12 plus negative 12. That's actually going to give us 0. So we could actually skip right to the answer right now, because 0 divided by some positive number is obviously going to just give us 0. But I'll just quickly fill in the magnitudes here. So finding the magnitudes of u and v, we get the square root of 40 for both of them. Not even going to bother simplifying those. So let's go ahead and plug those in. We get theta is cosine inverse of u dot v, which was 0, over the square root of 40 times the square root of 40. And once again, we can probably just skip to the answer kind of right here, but let's just simplify it. That's going to be cosine inverse of 0 over 40, because the square root of a number times the square root of that same number, the square roots essentially cancel off or add up to an exponent of 1. So all we have to do here is cosine inverse of 0. So cosine inverse of 0 is actually going to give us 90 degrees. If we think back to it, that means cosine of 90 degrees equals 0. So that angle is actually a right angle, which makes sense if we look at it. It does look like that's a right angle. So the property here, the important property, is if we get a dot product of 0 between two vectors, then that means cosine of theta equals 0, and this should say just theta. So the dot product is 0, that means cosine of theta is 0, which means theta will always be 90 degrees. So what this means is that A and B are perpendicular vectors, and another word for perpendicular, and the word that we'll be using more often than perpendicular, is the word orthogonal. Okay, so that is it for this chapter.